So good afternoon, everyone. It's my pleasure to share some of the work Stanford has been doing, both in the Doerr School and across the university, on how to build better batteries faster. Let me just highlight two very important trends that's driving battery technologies. Number one is the increase in the variable electricity generation. If you look across the board, wind, solar, concentrated solar power, all of them are reaching cost parity and below with conventional fossil-based electricity today. And this creates a requirement for storage in order to make renewable electricity available 24/7. The other big trend is the electrification of transportation. If you look at these numbers, they're just enormous, reaching 25 million electrified vehicles today, with a significant fraction being battery electric vehicles, meaning all batteries. And this, again, points to the need for better batteries. So let me say a little bit why this has been a challenging task. If we take a look at the research and development and the deployment of battery technologies, you have a very time-intensive process. You have to start from mining to chemistry to manufacturing to integration and then to recycling. At every single point along the way, you have to optimize, you have to down select, you have to iterate. And if you think about the characteristics of a battery technology, it encompasses a very large design space because it's chemistry. They are typically wide varying. They're difficult to manufacture consistently. Batteries are supposed to last a long time when they're good, so the assessment time is long. And they have to be safe, which means we have to understand rare events. If you take all of these factors together, it gives you an R&D cycle time, just R&D, of about 10 years. If you count the deployment time, it's even greater, on the order of 15 years. And I would argue we do not have the luxury of this time anymore going forward as we iterate to design the better batteries. So today I'm going to tell you about how we can do it faster. Let me now say another challenge as a material scientist. I like to think about why the chemistry of a battery is so challenging. It's because of the scale. We have to span not only scale in length, but also scale in time, and also scale in energy. Let me impress upon you this scale in energy that we must span. If you take one of these batteries that you can find in an electric vehicle, and you simply go down the scale, and you think about what's inside at the millimeter level, at the micron level, at the nanometer level, at the atomic level, you go from watt hours to picowatt hours, 10 to the minus 12. And then if you think about how much energy storage you need to decarbonize, transportation and the grid combined, approximately 200 terawatt hours. So you're going from 10 to the minus 12 to 10 to the plus 12. 24 orders of magnitude of energy must be spanned. This is why it's so challenging. So let me offer a take-home message slide first. I'll come back to this at the end. How do we build better batteries faster? Well, number one, we have to really innovate across disciplinary boundaries, academia, entrepreneurial, industry. Number two, we have to appreciate battery as a system. And we have to work backward from the solution at scale. So we have to work backward from the need for 200 plus terawatt hours. We have to accelerate the learning cycle, so the 10 plus years I mentioned. And then finally, we have to understand the science of safety and reliability, because we have to make billions of these devices that's safe and reliable and repeatable. So I hit each one of these in several brief vignettes of research across Stanford that Chueh and I had the pleasure of assembling over the past several years. So on the first point, innovate across boundaries. If you take a look at the innovation needed for batteries, it goes all the way from atoms to devices to systems. And this is a plot showing you all of the time and length scales you must master. And through the efforts of the past 4 years, starting with the Precor Institute for Energy Other and Runes leadership, we assembled 2 initiatives to bring people together at Stanford, the Storage X initiative, and also the Slack Stanford Battery Center that was launched this year to coalesce activity between Stanford and the Department of Energy. We have now over 25 faculty members actively working in this area, some of whom are in the room. And this has been a very fun exercise to connect the boundaries from the School of Engineering, the Doerr School, the School of Business, and so forth. Another very exciting part of the boundary is one that extends beyond the boundary of campus into Silicon Valley. I just want to highlight 2 things that's really awesome. Here in our ecosystem, for companies that spun out of Stanford or started by Stanford faculty, students, and postdocs, we now have a fully integrated supply chain for batteries just within our family of companies. In batteries, from cathodes to anodes to electrolytes to solid-state electrolytes in one vertical chain. We've also, as of this year, achieved integration horizontally, looking at energy storage electrochemically, chemically, thermally, and mechanically. I like to call this the Stanford portfolio of companies. And why is this important? This is a revolving door. We interact, we advise, we participate in these companies, learning about the real scientific challenges that folks are experiencing on the front line of deploying, transforming a technology into a product. And this information comes back to us here at the university to help us guide the next round of investigation. Number 2, I want to talk about working backward from scale. And the key question we have to address here is what to build. What do we build so that it can achieve the terawatt-hour scale needed? We have been developing a framework to combine mineral availability, supply-demand dynamics, technology complexity, and policy drivers to predict technology learning curves. Because what we want is not only to know the starting point of a technology in terms of cost and performance, but we must also predict 25, 50 years from now what it will look like. If you look at lithium-ion batteries, it started well over $2,000 per kilowatt hour, and now it's just hovering around 100 at the battery cell level. So let me just share with you one such prediction. We recently asked the question, since lithium, it is not so easily mined in today's technology, what if we switch to sodium? Very abundant. Once we did this analysis considering all the factors, you can see this black curve coming down, that's lithium-ion batteries. And this red curve is sodium-ion batteries. And the result was rather surprising. We thought we would find that sodium-ion will be a clear winner. But if you consider it as a system, not just as a battery technology, but a battery technology that needs to be deployed at scale and manufactured at scale, then you get this red line, and you actually see the 2 curves barely intersect, telling us that even for a technology that has a superior cost floor because it's sodium rather than lithium, you may still have difficulty reaching it. But this is not all bad news. It tells us where we can intervene. What can we do from the policy side, from the technology side, to bring the curves together to reach parity in terms of cost faster? This is a zoom-in plot showing you how close those curves got. So this is a very interesting study telling us thinking purely about replacing lithium with a much more abundant element may not be the immediate obvious solution because of the complexity of the system. So this is the second point of what to build. The third is about learning cycle. The technology learning curve we saw on the last slide occurs because we're able to iterate many tens of thousands of times in the lab, in the factories, and so forth. And this is one depiction of a cycle of making changes, measuring the effect of the changes, and designing new experiments to optimize to achieve the goal. And this is a very time-consuming process, often taking 6 to 12 months. And one of the recent accomplishments here at Stanford with my colleagues, we are using the power of artificial intelligence. We're using the power of advanced metrology to speed up the learning cycle. Let me highlight a few examples. One of the challenges of making a better battery is navigating this intractably large chemical design space. You have the periodic table, that's your friend, but the number of permutation is hopeless. So here, in one example of work between a colleague who sadly is no longer with us, Evan Reed and Chueh, they were investigating how to down select from 12,000 different materials used in a battery, and using machine learning to narrow down based on the desired properties to 21. And this can be done extremely efficiently for the down selection. Another example, 38,000 battery materials selected based on their characteristics, and then down select to just 2 using artificial intelligence. Yet another example also from East Group, looking at how to down select molecules for batteries that would enable much higher energy density and safety. And these are examples of how we are navigating very large chemical design spaces. Beyond navigating large design spaces, we also have to think about predicting into the future. If your batteries work well, they should last you about 10 years. Well, we don't have 10 years for our learning cycle. How can we compress this down to 1 week, for example? This is one depiction of how batteries perform as you age them, okay? And the job here is to find ways to predict when the battery is going to fail using as little data as possible. And this is a very challenging task. And here I'd like to highlight work from myself and also from Simona Honore in the Doerr School to use artificial intelligence to correlate all the complexity of battery aging mechanisms. And the goal here is not only to predict how long the battery is going to last, but exactly how it's going to fail. Because if we know how it's going to fail, we have the opportunity to address the root cause in the iteration to engineering a better battery. A lot of time people think you can represent battery by 1 or 2 numbers, like how many years it's going to last or how many times you can recharge it. It turns out when you use a data-driven approach, you have about 100 different numbers that represents how a battery is going to behave. And this is really the power of a data-driven process to understand and to provide actionable insights. This is done not only in laboratory conditions, but we're also now able to extract real-world conditions and predict how a battery might last in your car with very little data at hand. And this is now also being used to accelerate the learning cycle. The final example I want to talk about is the science of safety and reliability. A well-engineered battery doesn't have any safety issues. The failure rate is on the order of 10 parts per million. It's very difficult to measure. So really have to turn to advanced tools to understand how failure occurs. I want to share one cool video with you. This is taken here at Stanford to look at how lithium could short circuit the battery. So it looks a little bit overwhelming, perhaps coming from science fiction, but believe me, this is no science fiction. This is happening undesirably in your battery if you're unlucky. And we are understanding how this occurs. But this is not done only by making good measurements, but also by combining with good computational modeling. And my colleague Hamdi Chalepi and Daniel Tartafosky in the Doerr School are complementing these experiments with simulations to understand what's happening. And this is then allowing us to understand the science of failure. So this brings me to the end of my presentation. I'll just put the slide up here and quickly repeat. Crossing these interdisciplinary boundaries is absolutely critical, not just across different schools and departments at Stanford, but also across the Silicon Valley boundary. We must appreciate battery as a system, and we have to work backward from the skill that is needed, not from the skill we have today. We have to accelerate the learning cycle, and we have to understand how to make batteries safer and more reliable. Thank you.